This is problem number 6 on the practice problems for test number 2. A tank filled with water has a rectangular bottom that is 20 feet long and 10 feet wide. Its top is also rectangular and is 20 feet by 5 feet. The tank is 15 feet deep vertically. Its top is 30 feet below the surface of the ground. Find the work done in pumping all the water in the tank up to ground level. Note, water weighs about 62.4 pounds per cubic foot. You should clearly show the integral that you set up to answer this question, but you can evaluate it numerically with the calculator. So the first big part of this puzzle is to try to come up with a nice drawing, a good 3D drawing on your 2D piece of paper that captures the relevant characteristics of this tank. So here's what you're focusing on. You need to draw something which is a rectangle at the bottom, 20 feet by 10 feet, and at the top is also a rectangle, but 20 feet by 5 feet. Don't worry about the depth of the tank. Don't worry about it being below the ground. Just see if you can draw something that captures those things. Pause the video here and then come back once you've got a decent picture. So here's what I've come up with. I'll go ahead and label this thing with its dimensions. So the base is 20 feet long by 10 feet. That's at the bottom of the tank. And then the top of the tank is also 20 feet, but this one is only 5 feet instead of being 10. And so I'm imagining kind of looking at this tank from above and a little bit in front of the tank, trying to give it that 3D feel. To what effect, I'm not sure. But let's see if we can go ahead and start slicing this thing. So what we know is that the work done when you raise a slab of water in this case is equal to force times distance. So we're going to use this idea and just kind of expand it until we get to something reasonable. So we know that the force is the weight in this case, so we don't need to do MA. We've got force being mg. Force is weight times distance. And I'll put in here, it's the weight of the slab times the distance a slab moves. So what we're really interested in knowing here is what kind of a slab are we talking about? So the idea is we're going to take that tank and we're going to mark up the picture. So I just paused the video there so I could copy and paste my tank drawing. So we're going to go ahead and cut this thing up into slabs of water. And the idea is you want to cut the tank into up in such a way that the slab, the molecules in any given slab, travel about the same distance. The weight is the weight. We'll figure that out. But really the important thing is that you are grouping together molecules that travel the same distance. So it seems like there are a couple of natural choices for the slab. Maybe you can draw a vertical slab, so something that comes up this way and then goes over to the right and then goes down and then in the bottom of the tank, something like that. But the difficulty is that, for example, if you pick a drop of water that's right here and you transport it straight up to the ground, it doesn't go as far as a drop of water there, and it goes further, I guess, sorry, I said that backwards. It goes further than those drops of water and doesn't go as far as these drops of water. Everything has to get to ground level up here. So that kind of a slab is not good because the molecules of water in that slab don't all travel about the same distance. They travel wildly different distances. So if a vertical slab doesn't work, then it seems like maybe a horizontal slab is in order. So we're going to go ahead and draw a horizontal slab. I'll draw it here in blue. So basically the idea is that you just pick a random point that you're going to draw horizontally, a slab that cuts through this water, and then we'll go dotted back there. Something like that. So that right there is a horizontal slab of water. Imagine giving it a little bit of thickness, so it's not like razor thin like I've got here, but just a little bit of thickness. I'm not going to draw any more on that slab, but the idea is that any molecule of water in this slab, if you bring this molecule of water straight up, or if you bring this molecule straight up, or this one here in the corner straight up, they all travel about the same distance. And the only reason it's not exactly the same distance for all of them is that the slab does have a tiny bit of thickness, but they should all travel roughly the same distance. So next thing we need to do is start calculating, according to our black equation here, we're trying to figure out the weight of the slab and then multiply by the distance. So it feels like we need to introduce a variable here. So how about we say that x is the distance off of the floor that this slab is. So from here straight down is what we're going to call x. So that distance right there is x. And then that means the distance here straight down, well, that was given in the problem, was 15. That was the depth of the tank. So let's think about how far every molecule of water in this blue slab has to travel. So first we have to get the molecule of water, say just this random molecule of water, needs to get up to the top of the tank, and then it needs to go from there up to ground level. So how far is it to get to the top of the tank? Well, if it's currently x feet away from the bottom of the tank, and it's 15 feet to the top, then how much it has to go is 15 minus x. So that molecule of water needs to go 15 minus x just to get to the top of the tank. But then there's this other twist in the problem that said that the top of the tank is actually 30 feet below the surface of the ground. So every molecule of water has another 30 feet that it has to travel once it gets to the top of the tank. So that's the distance that every particle of water in every molecule of water in that slab has to travel, roughly 15 minus x plus 30. And then the other thing we need to know is the weight of this slab. So let's put that up here. So the weight of the slab is actually also going to have a couple of pieces in it. So we know that water weighs 62.4 pounds per cubic foot. So it feels like it's going to be 62.4 times something. And what is the something? Well, it's however many cubic feet of water are in that slab. So I'm going to write down here times the volume of the slab. So the next thing we need to figure out is the volume of that slab. So that slab is basically a big blue rectangle, but with a tiny bit of thickness. So all we need to do is write down the length and width and then the little thickness, the height of that slab. So let's see if we can put this in here. So the 62.4 I'll write in the front times the volume of the slab. It's a rectangle with a little thickness, so it's really just length times width times height. And then we'll clean up here in parentheses. That turns into a 45 minus x. And then the next piece here, let's fill in the easy parts first. So 62.4 times the length of the slab. I'll go ahead and call the length of this slab this purple one right here. I'll say that this right here is the length. But for every slab, that length is a constant. It's always the same length. In this case, it's 20. So it's 62.4 times 20 times, now the width is another story, because the width of this slab, I'll put it here in green, the width of this slab is that guy. But the width of the slab that's a foot higher than this particular blue slab is a little bit smaller. And the width of the slab of water at the very bottom of this tank is bigger. So we need to do some work to figure that out. So let's leave that as a blank for right now. Times, and then we need the height. So the height of the slab, the thickness of the slab, I didn't draw it, but we're imagining that blue slab has a little bit of thickness, and we'll go ahead and call that delta. And what letter should we use? Well, look at the red X that we've got there. X is that vertical thing, so it feels like delta X is a natural choice. Again, I don't want to label it in the picture because it's already cluttered enough, but I think that's good. And then we copy this, and all that's left of us is to fill in the blank there. We just got to find the width. So the idea here is that the width is going to have something to do with X. Again, we had said if you're at the bottom of the tank, then the width is going to be the entire thing, the entire 10 across, that's this 10. But if you're at the top of the tank, the width is only 5. And if you're at some X in the tank, then the width is going to be some function with X in it. So you might be able to just kind of use the idea of similarity to figure it out. I'm going to give you, if that's not intuitive for you to use similarity, I'm going to go ahead and give you just like a formulaic, a kind of technique to do this. So I'm going to go ahead and make a chart here, X, and then the width of the slab. So let's just fill in the two slabs that we talked about that are easy. So if X is 0, that is to say we're at the very bottom of this tank, then the width of the slab is the entire width of the tank at the bottom, which is 10. if x is, if we're at the top of the tank, that means that x is 15, because the tank is 15 feet deep vertically. Then the width of the tank is the width at the top, which is 5. And hopefully you buy into the idea that there's a linear relationship between the x and the width. So all we need to do is come up with the equation of a line that hits those 2 points, 0, 10, and 15, 5. So let's just do that real quick. So instead of y equals mx plus b, it feels like this should be w equals mx plus b. And the b is given to us. So w equals, the b is 10, because when you plug in 0, you get 10. So this is something plus 10. And then there's an x, and then all we need to do is find the slope of the line that hits those 2 points. So the slope is the change in y over change in x, but in this case, it's a change in w over change in x. So how much does the width change? 10 minus 5. Divided by how much does the x change? 0 minus 15. Be consistent with the order that you subtract. 5 over negative 15 is negative 1/3. So that goes right here. So negative 1/3 x plus 10 is the relationship between the x and the width. And so then once we have that, we circle it and we stick it right up here in this blank space. So negative 1/3 x plus 10 goes right up here for the width. I don't have enough room. Okay, that's good. And that's the hard part, is coming up with that big, long expression for the work done to move all the molecules of water in a generic slab up to the ground level. And once we've got that written out, then it's just a matter of sticking a sigma in front of it. So I'll write this step. You don't really need to. You could just go right to the integral if you want to. But let's see, did I write that that was the work for one slab? Yes, I did. So we just calculated the work to move one slab of water up. So if I want to do the work for all the slabs, what I need to do is add up the work for each single slab. So that means adding up the expression that we just had up above. So that was a 62.4, and there was a 20, and then negative 1/3 x plus 10. Length, width, height was the delta x, and then the distance the water traveled was 45 minus x. And let's double check that we got all the pieces right. I think that's good. Okay, and then just a little detail. I'm not super needing this, but technically all the x's get indicized. I don't know if that's a word, but we just number the x's so we can talk about having like a discrete number of slabs, add them all up, but then when we actually find the work done to move all of the water, it becomes an integral. So it's the integral of 62.4 times 20 times negative 1/3, and then we get rid of the funny i's that we just introduced. Delta x, I'll put at the end as a dx, and then 45 minus x, getting rid of that I as well. And then the last thing here is the limits. So how much is x for the bottom slab and how much is x for the top slab? So remember, we let x equal the vertical distance from the bottom of the tank to the slab in question. So for the bottom slab, x is 0. For the top slab, x is this distance, which is 15. You don't let x run from 0 to, say, 45, because there's no water up there once you get past these 15 feet of water. So 0 to 15 are the limits. Okay, and you can actually do this integral pretty easily without the calculator, but we'll just type it in. Okay, so we just need to type all of that very carefully. 62.4 times 20, parentheses, negative, that's not the negative, negative 1/3 x plus 10. Close those parentheses, new parentheses, 45 minus x. think that's looking okay so far. Close those parentheses, comma x, comma 0, comma 15. So if we typed everything correctly, then hopefully we'll get a number that makes sense. It's hard to know what makes sense in these kinds of problems, but I think that number at least agrees with the answer key. So 5,382,000. Okay, so since we did stuff in pounds, I can't even tell you what the unit of measurement is. When pounds are involved, you can look it up. If you are so inclined, you could actually just write down what the units are for each of these pieces. For example, this was 62.4 pounds per cubic foot. And if you just write down what each of the numbers represents, like that 20 was at 20 feet, I think you'll end up with some unit down there, which apparently represents work when you're in pounds. So I think that's it. These problems are definitely tough. Drawing a good picture and then coming up with a nice labeling system. You got to come up with a nice slice. In this case, it was that horizontal blue slice we drew, and then labeling X, that's an important part of it. The reason I like these questions, even though they're tough, is that you know, there's no just generic formula you can use that says, all right, this is how you do every single work problem. You really do have to take this problem and, you know, just figure it out basically from fundamentals, and look at the work done to move one slab and then stick that into a summation, which becomes an integral.